this is ZuriHac2023.
So for our first talk, we have Simon Peyton Jones, who doesn't really need an introduction. I think everyone here knows him. I will say some words anyway. He's one of the leaders of the Haskell community, both on a technical level as well as a community level. One of the lead designers of the Haskell language that we all use. And today he's actually going to talk about maybe the next big thing, which is Verse, a programming language that Simon has been involved in designing. So, Simon, we welcome you to the stage.
Okay, thank you.
And
Thank you. Well, good morning, ZuriHac. I hope you are going to have a great weekend of furious hacking by the lake. I'm so envious of a university campus where you can go swimming between lectures, and I have. So as many of you will know, I have a new job. I work for Epic Games now. And Tim Sweeney, who is the founder, chief executive, and author of the Unreal Engine, is a kind of uber geek boss. And he's happy for me to spend some of my time doing Haskell, so I do, so this is great. I'm going to tell you a bit about the thing that I've been working on with Tim for Epic, in the sort of Epic part of my time. I'd love it to have first to be a bit interactive, right? So if you can ask questions as we go, just sort of shout them out. I'll repeat the question so everybody can hear. I don't want to sort of, if we have to wait 30 seconds when everybody puts their hand up to get a microphone, it's not as free-flowing. So just ask a question. If I fail to repeat the question, tell me, and I will fix that, okay? But it'll be much more fun for me if you talk to me as we go, okay? So here we are. What's the time? 10:11. Right. So we have 60 minutes on Verse. Here's the picture. Tim is Epic has been very successful with Fortnite, a game that you may have played even. But with games companies, there's always a question about what's the next big thing. So Tim, for a long time, has been talking about the metaverse, way before other people were talking about metaverse-y kind of things. So for him, the metaverse is about shared social interaction in an immersive 3D environment. What I like most about his story about the metaverse is he thinks of it as a kind of open economy, not as a kind of walled garden, right? He wants it to be, he wants the metaverse to be like a motherboard in which you can plug your little circuit board and do wonderful things based on a substrate, right? So it has rules, but it's an open economy in which other people can flourish. And internally within Epic, one of the things I like is they send us every 3 months we get an email saying, and this is the amount of money that we have given to third-party developers. It's actively a thing of pride in Epic about creating a community in which other people can flourish. It's one of the things I like about working for the company. So, but this is quite an ambitious story, right? So in the end, you need some kind of computer that's going to run essentially forever, and bits of software are going to arrive and leave. So it's not just separately compiled, separate little apps that run on some platform. Everything's got to interact together. And so that means that there's a lot about open standards, and Tim cares a lot about writing open standards, not for low-level things like shaders, but essentially for everything, so that you can build something in not just Unreal, but in Unity and have it work in this metaverse. So I know nothing about all this stuff really, but this is the kind of context. So then Tim is building a new language to be the language in which you express the behavior of the bits of the metaverse, the machines or the avatars or whatever you have in your metaverse-y, immersive 3D virtual reality. And of course, we could use an existing language, and that would be the default option. But Tim has spent 2 decades thinking about his vision for what programming should really be like. And Verse is essentially an embodiment of his vision, right? So, and here is what he wants it to be able to do. He wants it to be scalable to run code that is written by millions of programmers who do not know each other, right? Not a single integrated team, but who do not know each other, that works over a period of many years in a computer that never stops and supports billions of users, right? It's very, there's a strong emphasis on transactional memory. I'll say a little bit more about that, and very strong interop guarantees. So I think this will be tough to maintain, but what he wants is that if you write something and it works, it will continue to work. And of course, that's easy to say and really hard to do, but that's the goal. We'd also like it to be, since we want this to be written not just by hardcore developers, but even by end users, meant to be sort of easily learnable and somehow extensible as well. This is a pretty ambitious prescription for a programming language, right? And we'll just have to see how well we sort of deliver on all of this. But I like working for a place where at least the aspiration is substantial, right? Now, just make me say a little bit before we get to verse itself about transactions. So many of you will know that there was a sort of hot phase about software transactional memory about 10 or 15 years ago. It was all over the, lots of programming languages. Microsoft made quite a big investment in software transactional memory. But in the end, the place that software transactional memory flourished was in Haskell! Haskell! Yes! That is the place. Because, why is that? Because when you do transactions, you have to log reads and writes. And in an imperative language, there are a hell of a lot of reads and writes. But in Haskell, when you do reads and writes to transactional variables, they're very few. So the overheads of transactional memory are much lower in Haskell. Same in verse, right? Because verse is a declarative language. So, but here, Haskell's STM, which comes in the box, which sort of works within one processor, right, in a shared memory environment. Verse's STM is going to work across a data center, and that's wildly ambitious. This last bit is Tim's words, just a dream and a prototype at the moment, but we're trying to do lots of crazy stuff, and this is one of the pieces of crazy stuff that we're going to try to do. Okay, so that's the sort of the big picture. So the plan for executing on this is to build an aeroplane and make it take off at the same moment that you're doing research on the structural properties of aluminium or titanium. So Epic has already released Shipverse, which is a programming language that doesn't involve the sexy features that I'm about to show you, but is nevertheless executable today to build games in and do virtual reality kind of programming in. And it has a whole team of developers and software community, all of the usual stuff you'd expect with a corporately supported language. And at the same time, there's the MaxVerse team, which is what I'm part of, is trying to reverse engineer verse out of Tim's head. I'll show you a bit more about that in a second. And the idea is that Shipverse is going to become MaxVerse over time. We just got to make sure that the two finally line up. Okay, so we're simultaneously doing what turns out to be quite a substantial research project at the same time as shipping a language. So it's just slightly scary to me, if we don't prove this theorem in time, will the airplane fall out of the sky? Who knows, but that's the prospectus. Okay, yeah, Ben.
How long has Shipverse been around?
How long has Shipverse been around? It was actually released about 3 months ago, something like that, very short time ago. So if you just search for Epic Verse, you'll get to this page very quickly. So you can download it before the end of this session. Right, okay. So last thing to say by way of setup is that this whole project is meant to be very open, right? Verse as a programming language, it will be an open source programming language. We're not ready to, release an open source implementation yet, but we will, right? And there's going to be a paper at ICFP that embodies most of what I'm going to talk about in this talk. So it's not a kind of, secret language that we'll let you into. It's meant to be, like Haskell, a kind of open source language in which we hope that a big community of people will participate in. It's at a fairly early stage at the moment, so that makes it more difficult to participate, but that is the clear goal. And Tim's completely signed up to, offering the compiler and the verifier and the runtime, all under very permissive open source licenses. So I'm quite pleased about that too. Okay? That's the end of setup. Any quick questions about that? Oh, yeah.
What is the verifier?
What is the verifier? The verifier is the type checker. Right, so Verse's type system is, as we'll say a little bit about in a sec, pretty weird, and so the type system is strange to the extent that you might say I'm doing verification rather than doing type checking. Right, now, so now to MaxVerse, and this is the project that we're on to. So Tim has literally been, Tim is a sort of autodidact. He's taught himself a lot about programming languages. He's read tons of papers. And he's been thinking quite deeply about programming languages for a long time. So there's all this stuff going around in his head. So he actually has a very clear vision of what verse is. But he's also been running a business and building, immersive 3D virtual reality. So he hasn't really had time to write any of this down. So the name of the game for my job is to sort of suck out of Tim's head what verse is. Because if you look at a verse program and say, I wonder what that does, and the answer is, well, we better ask Tim. That doesn't scale very well to those millions of programmers, right? So we need to write down a spec for what this language is and what it should do. And so there's a team, so Leonard Augustin, I mean, these are names you will recognize, right? So Leonard Augustin works for Epic. Kuhn Klassen and Ranjit Jalla and Stephanie Warwick are on sort of part-time contracts. Even Guy Steele is working with us on Proving Confluence for Verse. So it's a pretty awesome collection of people are working on this, sometimes with university jobs as well, sometimes like me and Leonard, actually full-time for Epic. And, but nevertheless, our experiences, we have conversations with Tim 2 hours a week on the phone. He's the CEO of a $1 billion company. He spends 2 hours a week talking about denotational semantics with these geeks. It's amazing, right? But what happens in every conversation is we start like this and we finish like this. So our job is to try to make sense of the huge pile of spaghetti that comes out. And interestingly, I think there is a lot of very interesting ideas in verse, and I'm hoping to convey some of them to you in this talk. This talk is it's very similar to the one that Tim and I together gave at Lambda Days a few days ago, and to the Haskell Exchange call I gave. But I think not all of you will be there. Things have moved on a bit since then, and also verse is sufficiently weird. It's fine to hear it twice. Actually, I need to hear it repeatedly. Okay, so you ready? Fasten your seatbelts. Verse 1 is just a sort of quick overview of the familiar bits of verse. Now, verse is a functional logic language. So it's a declarative language in the sense that a variable gets one value. It's not like a mutable cell that changes its value over time, right? So it is in that sense a language that you will know and love. And it's a functional logic language, so it has functional programming as a subset. Every functional program is a verse program, if you like. The lambda calculus is a subset of verse. So far, so familiar. It's not a strict language, nor it is a lazy language. It's a lenient language, meaning most things get evaluated eventually. I'll be a bit more specific about that later, I hope. And it has a very strange type system, or an unusual type system, which I enjoy a lot, and will not have time to say very much about. And it also has an effect system, right? Because rather than doing, though it's declarative, right, it's very careful about effects, but instead of using monads to plumb them, it has a kind of effect system because it's careful about order. We'll see a little bit about order. So quite a lot of these things I'm not going to say very much about, but I'm going to concentrate initially on the core that we've, the core sort of computational concepts. What is functional logic programming and how does it work? Okay, so first sort of familiar bits. It's got sort of standard looking values, right? So, and a sort of expression sublanguage. So 3 is a verse expression, 3 plus 7, it has tuples that are also called arrays. So tuple and array in verse is pretty much synonymous. And you can index into arrays with this, square brackety thing here. And down here, this is just to say, 1 or 2 slides, you may see this, because if you write 3 with parentheses around it. How do you write a singleton tuple in Haskell? In Haskell, we barely have singleton tuples. The compiler has it inside. But in verse, singleton array is quite important, just an array with one element. So you can write it with this more noisy syntax. But round parentheses just mean the same thing. Okay, except for you have to write the noisy syntax for singleton. Okay, an empty array is array open close. Okay, now, what else? So bindings, so instead of let, is just this colon equals and semicolon notation. So this is like let x equal 3 in x plus x. You can have multiple bindings, and they can interact with each other. So you can think it's a bit like letrec. And here I put in this second one I put the binding of y before the binding of what have I done? I put the binding of x and mentioned it before. So bindings can refer in both directions. Order doesn't really matter here. Okay, and then you're going to have function definition, so it's a fully higher order language, natively higher order. This is lambda, so lambda is written with an infix fat arrow rather than a lambda and a dot like in Haskell. But you can also write function definitions in the source language by putting the pattern matching on the left, just as you do in Haskell. This says f is a function of type int that returns an int and it returns x plus 1. Okay, and then this semicolon, that's the end of f's definition. Here is a call of f applying it to 3. Okay, so far so good? Pretty, there's just ordinary functional programming. Yes? Are the type annotations required? They are on, let's see, they are, yes, they are. I mean, yes, they are, but they can be any. So any is a type. Yeah, but I'm not going to get too much into types, but yes. Okay, finally, the definitions can be recursive, and we have conditionals, so here's just an ordinary definition of factorial. Okay, so far so familiar. Good? Nothing very exciting. So, now, yes?
Can we have the signature separate from the...
Oh, can we have a signature separate from the function definition? So in Haskell, you say f colon colon int arrow int, and they say, no, in verse you don't do that, for whatever reason. So, yeah. I'll ask you, this is one of these, yes. I rather like that you can write a signature separate. You can, actually that's not, no, that's not true. You can, no, you can. You can say f has this type, and then separate, Yes, I'm gonna, so I'm more familiar with the sort of, the core language. This is a surface language kind of question. Actually, on reflection, I think you can get very close to that using existentials. I'll show you shortly. So ask that question later. We'll see. You're going to see. Yeah. Where'd you go?
So could we have x of type variable a returns?
Oh, do we have polymorphism? Yeah. Yes, absolutely. Certainly you have polymorphism. In fact, we have way more than polymorphism. It's a sort of really, dependently typed programming language. Like I say, the type system is quite rich. I've got a slide about that at the end, but I can only do so much in a 1-hour talk. So the type system is one of the most fun bits. But we've got to get... Yes, to say, since we want to say well-typed programs don't go wrong, we have to know what going wrong means, which means we have to have a semantics for a kind of untyped language. So that's what we've concentrated on. So, choice. So this is the first time something interesting has happened here. In a functional logic language, an expression can can return one value, or it can return 2 values, or 3 values, or 0 values. Right? So in Haskell, an expression denotes 1 value. In verse, an expression denotes 0, 1, or more values. Okay? So that's a big shift of perspective. So here, 3 denotes a single value 3. This choice thing, 3 vertical bar 4, that vertical bar is the choice operator, denotes 2 values. Actually, it's going to be a sequence, not a set, something I'll come back to. False is a funny way to say 0 values. It's slightly quirky. There is a reason why it's written why it's spelled like that. I just pronounce it fail, meaning return 0 values. Okay, and there's some notation for returning multiple values, like 1.10. Okay. Now, bindings can you can bind a variable to one of these multiple value things. So let's see here. X gets to be 1 or 7 or 2. And then I want to return x plus 1. Now, this does not mean bind x to some kind of funny multi-value and then compute with it. Rather, it means successively bind x to 1 and then 7 and then 2, and execute the bit after. So then here, this bit here is very like a list comprehension. It returns all the x plus 1s, where x is drawn from this list. So it's as if, in verse, list comprehensions are, instead of being a kind of something we program on top and then desugar into something lower level, list comprehensions are part of the computational fabric of verse, okay? The very thing that computation means. And so, just like in Haskell here, x here is always bound to an integer. It's not bound to a list of integers, right? So in verse here, x is not a multi-value. X always has a single value at any one time. So it's very important. Right, yeah.
And so the types have no sort of indication of how many values...
The types do not have an indication of how many values. X has type int, and it is not multi-int. This x here, in Haskell, this has type int. This list has type list of int, yes. But in fact, in verse, there is no type for and a multi-value of, yeah.
And so is there any way to say, you lose some expressiveness there, right?
Is there any way to say this expression returns multiple values? No,
one value.
Or a single value, yes. Can you say an expression returns a single value? Yes, you can, but it's part of the effect system, right? The multiplicity of results is thought of as an effect rather than as because types classify values, and there are no values that are these multi-value things. They are simply not values in the language at all. So it's an effect. So choice is an effect, effectively, yeah, as it were. Yes, David.
Is this the same as or different from what icon does?
It's very similar to what icon does. I didn't repeat the question, but the semantics will do. In fact, you see that in a couple of slides' time. This is bits of this are identical to icon. Yeah. For icon, it was a language that was born and died before most of you were even thought of, right? So it's a little us old timers, icon. Okay. Anyway, yes. So now, what do you think this does, right? It's just like a Haskell list comprehension. We pick x iterates over 1 and 2, and then y iterates over 7 and 8. At any moment, they both bound to a single value. So, of course, you get 4 values out of this, just like the Haskell list comprehension. Completely, just what you would expect. Is that all right? Yeah? No surprises here, once you've got the list comprehension idea. But these choices also, what happens if you, let's say, make a pair here, with 1, 2, and 7, 8 in a pair. Does that make a pair with 2 multi-values in it? Absolutely not. It makes a it's a choice of actually one of 4 tuples. And this plus operation here, what does it do? Well, it doesn't add 77 to a 1, 3 choice. It's the same as the choice of 77 plus 1 and 77. So all choice is always floated to the outside, right? I keep emphasizing this, that multi-values, these choice things, are not values, right? They're always floated to the outside. Variables and values have no choices inside them. Okay? And that means that 77 plus false, how many values are in false? 0. So 77, so if you say 77 and add it to all of 0 values, you get 0 values, right? So it means the same as false. Good? Okay. Now, there's something a bit funky is happening here. So this is the kind of program at which you think, we better ask Tim, right? Because now things are not so straightforward, and this would not be a legal Haskell list comprehension. Look, if I write this list comprehension at the bottom here, right, x is drawn from the list y2, and y is drawn from the list 7, 8, GHC will say y is not in scope here, all right? But in verse, this is absolutely fine. What do you think it does? Yeah.
What about the recursive do in Haskell?
What does
Recursive do.
What does recursive do in Haskell? Oh, right. Yes, if you did a sort of recursive do with an mdo, it's that kind of thing that goes on. But again, it's built into the fabric of verse. So, it's in a way, it's easy enough to say. What does x? X iterates over y and then 2. But we don't know what y is yet. And then y iterates over 7 and then 8. So the first pair is going to come out as be y and then 7. But y is 7, so that's 7, 7. Then we get y but we're iterating over y more quickly, right? So the next value of y is 8. And so that first component was 8. And then the other ones come out. So this is a bit funky, right? Is this this is why we need a semantics. We've got to say, does this program make sense? Is it rejected? Is it deadlock? Or does it compute and produce values? So I don't want you to stress out too much about this. I just want to point out that already we get into some slightly strange things, okay? Now we get to icon, right? So with conditionals, usually if you have a conditional, that E would return a Boolean, but not in verse or in icon. E returns, remember, 0 values or 1 value or more values. If E returns 0 values, we take the else branch. If it returns 1 or more values, we take the then branch. All right? So it's kind of an economy of concepts. It looks kind of cute. We get away without having Booleans, but it turns out to be really quite useful and compositional. So that tells us something about greater than. So what must greater than do? Yes?
So if the number of values is not in the type system, does that mean that if can't have a type?
If the number of values is not in the type system, does that mean that if can't have a type? No. So remember I said that the number of values is part of the effect system. Right? So I suppose if you want to say, does this whole if return exactly 1 value? Well, it returns exactly 1 value if E1 returns exactly 1 value and E2 returns exactly 1 value. So you can reason about it in the same way. Yeah. At the back? Yep.
Is that the reason why it's called false?
Oh, is there a reason why it's called, is this to do with why it's called false question mark? It's sort of close. I'm just not going to go there, I'm afraid. I spent time arguing with Tim about this, yeah.
Question, but on the previous slide, what happens if you make them mutually recursive?
Oh, what happens if you make them mutually recursive? So actually, so long as you don't have something like 1 ... y, then it might get stuck, right? I'd have to think hard about that. But I think if it was y equals x vertical bar 8, I think that would be, yes, mumble. If it was, yes. I need to think about it. But that's why you need a semantics, right? You've got to have a way to answer that question. It's a good question. I'm not going to do it on the fly in front of everybody. And anyway, without the semantics, you just have to believe me anyway. So, yes.
What's for this construction? Is it from game design or?
What is what?
The motivation for this kind
What is the motivation for this? Oh, why are we doing functional logic programming? Good question, right? So I thought somebody would ask this at some stage, and it's an excellent question. So why do we do functional programming, right? Why, back in 1980, when I was in Cambridge and first met functional programming and was writing, lambda code with John Hughes at 1 in the morning in the computer lab, why was I doing? It was because it just seemed like the right way to write programs, right? And was it going to be a more productive way? I don't know, but I spent my entire professional life thinking, let's take this one idea and push it to a conclusion. So the answer really is, Tim thinks, and I think there's a fighting chance of this actually being true, that functional logic programming is just a better way to write programs. Now, our aim is to take functional logic programming, which is a kind of niche activity, right? It's a niche of functional programming, and functional programming is still, in most people's minds, still a niche, right? So it's a niche of a niche. We're trying to take that and kick it into the mainstream, right? And we have 350 million users of, Fortnite and so forth as our initial user base. That gives us a chance to be mainstream. But we shall see. I mean, it is in some ways a big intellectual experiment about, is this actually a better way to write programs? So my mission at the moment is to say, let's try to understand exactly what it is in full detail and try to make it as coherent, have a well-defined semantics, remove semantic warts, just make it as good as possible. And then just like the experiment with Haskell, which initially seemed wildly unrealistic to everybody else, they thought, what are you doing in your ivory tower? Here we all are, right? Writing Haskell code. So we shall see. We shall see. But it's a pretty exciting intellectual journey, and maybe one that has practical significance. Yes? Sorry, I didn't really, let me come closer and ask the question.
If we have a mutual recursion here, and then we have infinite series of results, would it still be a valid program?
Oh, if we have mutual recursion and an infinite series of results, would it still be a valid program? I'm not going to answer that question. You have to go to the paper and look at the semantics, right? Because these programs, can get, we haven't said enough of the language to be able to give a satisfying answer to that question for a bunch of people. So, sorry. And also, I don't know exactly what program you mean, but it's wildly expressive, this. And we haven't even got to the expressive bit yet. Yes. Oh, yeah. Are there infinite lists? No, you can have infinite choices. There's no, but it's linear, which means everything gets evaluated. So it's not lazy like Haskell, right? So the place you can let go of computation is like if the scrutiny of an if returns a choice of many things, right? It'll pick the first one and abandon all the rest. So there is some element of we abandon computation, right? But we don't have infinite data structures at all. Yeah, in the way that we do in Haskell. Yeah.
X takes multiple values, and some of them are greater than 20 and some of them aren't. Will if E1 is...
Oh, good question. Yes, so here, what if X here, or let's say if it was E greater than 20, if E returned multiple values, some of which were bigger than 20 and some not, right? Then what happens to this if? So anybody, so I've already told you the answer, right? Because look here, because if E1 returns one or more values, then we pick the then branch. All right? So X bigger than 20, if E greater than 20 returns multiple values, I'll compare each of those with 20. And if any of them succeed, that expression will return more than one value, or one value or more. So yes, it does it all.
So is X greater than 20, does that filter the elements out that are...
Does X bigger than, so if I take E bigger than 20, that is precise. So we take all of the values returned by E, pick the ones that are bigger than 20, and return all of those. So E bigger than 20 is filter bigger than 20 X's. Yes, at the back. Vlad.
Before we got Haskell
Louder, louder. I can't hear you.
I'm sorry. So, in order to make Haskell run fast, we needed STG. In order to make Haskell run fast, we needed STG to run it on stock hardware. But do we have any idea how to make this functional logic programming run fast on stock hardware?
No. So how are we gonna make this thing run fast? So I'm still on to what does it even mean, right? So then what we're going to do is going to say, look, so one advantage we have, unlike Haskell, it's not lazy, it's lenient. So for lots of programs, we're able to do enough data flow analysis to say, basically, this is a C program. We'll just generate machine code, right? If you do funky, weird things, it's not going to run as fast. And so we're busy, so that will, I think we'll spend a lot of time on compilation, but not yet. Right, so just tell me, anybody want to do this exercise? X less than 20, less than is right associative. So what does this expression do?
What's the domain of X? What's the domain of X?
Oh, let's say that X is an integer, just to keep it simple.
Set of values between 0 and 20?
It will filter out all the values that are between 0 and 20, because this X less than 20 will succeed if X is less than 20, returning X.
All the choices.
All of them, yes, and then we'll compare them with 0. So in fact, you can literally say if 0 less than X less than 20, then blah, which is what mathematicians do. So it's a bit cute. It's not the point, but it is nice. Yes, Icon could do this.
Won't this return a number of zeros equal to the number of X's that happen to be between 0 and 20?
Yes, it will return a number of zeros equal to the number of X's. Yes, so it will return a lot of zeros, but it doesn't matter because all you're doing is if. Yeah.
No, there's no if.
Oh, yes, sorry, there's no if here. Yes, all right, it'll return a number of zeros equal to the, yes, thank you. Yeah, over here, Andres.
So it's only like X is less than Y, but it's currently X of Y.
X is less than, so a less than returns the left-hand operand if it succeeds. That's the definition, okay? So yes, you can write some things and they won't work, right? You just have to know what it does. That's right, yes, over here.
What is it? In the place of 20, there are multiple values.
If it's greater,
On the right-hand side of the greater than operator.
oh, what happens if the right-hand side of the operator has multiple values? Well, I told you every operator, like plus and greater than, and all operators, right, that if either of the arguments or both have multiple values, we just iterate over all pairs of values, right? So just like less than is not special in that respect. No more than plus, or any function call. Yes, would you go?
So X is a choice of value, right?
Well, X is now, I have to say, X always stands for a single value, right, remember? Right? But if that was an expression E, and E was like 3 vertical bar 4, yes, okay, so.
The question is, will the then branch have all the succeeding choices of X and the else branch have all the failing choices?
Will the then branch have all the succeeding values of X and the else branch have all the failing ones? No. I just said, if it returns one or more values, we take the then branch, and that's it. We don't take the then branch many times.
I think the question is, what if X appears in E1 or E2?
Oh, what if X appears in E1 and E2? We'll just pick the, and remember, if it is a variable, it has one value at any one time. So somewhere earlier, right to the left, we might have said X equals 3 vertical bar 4. In the 3 iteration, we'll say, is X bigger than 20? No, so we'll pick the other. So yeah.
The then branch actually runs for each X.
The then branch will, that's right, so the question is, will the then branch run for each X? When X is a variable, and therefore we're running this whole thing for each value of X, then indeed the then branch will run for each value of X. But if it was E bigger than 20, and E was something like 3 vertical bar 4, then it will only run once. Yeah, yes?
So when you write verse, you have to be really careful if you write X greater than 20 or 20 smaller than X.
When you write verse, you have to be careful whether you write X bigger than 20 or 20 smaller than X. Yes, you do, because that will return a different value. But of course, if you're checking a Boolean in an if, it doesn't matter. But in other contexts, it might matter. Yes. Over here?
In Haskell, you could write an if function that has the same semantics as a built-in if. Is that true for verse too?
So in Haskell, you can write an if function as the same semantics as the built-in if, because Haskell is lazy. Verse is not lazy, so no, you can't. So lazy, it doesn't have that degree. Okay, so I'm going to skip this. Right, because I want to. We're gonna run out of time. So this is a lot of fun. You're asking all the right questions, and you're exactly explaining why we need to have a semantics for this language. But we've got to get to the semantics. So now, a very unusual feature of verse for a functional logic language is that you can take choices and turn them into tuples or arrays. So there's this for construct that takes an arbitrary expression E and takes all the choices that E coughs up and reifies that, or concretizes it as a single value, an array. So for 3 returns a singleton array, for 3 vertical bar 4 returns an array of 2 values, for false question mark returns an empty array or an empty tuple, and for this 1.10 thing here will return a tuple or array 1 to 10, right? So this tells you, this is why sequence is important, right? So when an expression returns multiple values, it returns them in a particular sequence because we're going to construct an array which you could then index in and therefore discover which sequence it came back in. So verse would be non-deterministic if it wasn't precise about the order of the value. So very important, very big design decision in verse is that the order of choices is deterministic. Choice is not commutative, though it is associative. And in almost all other functional logic languages, they're sort of non-deterministic, and this choice thing is sort of floated to the outside of the whole program. And the sort of reifying things as values is thought of as a somewhat meta operator, whereas in verse it's deeply built in. Yes, at the back. Do we use the effect system to get commutativity some of the time? I don't know, not thought about that, so maybe, yeah. Do the types represent ordering? No. Yeah.
So if you bind the choice to a variable and then you for the variable, you only see the value.
Yeah. So if you say x colon equals 3 vertical bar 4, and then say semicolon 4. X equals 3 vertical bar 5, and then you say 4 curly brackets x, you will get successively a singleton 3 and a singleton 5. Yes. Yeah. So, yes, sort of binding a variable, sort of, that says iterate here. It's very, very, very good, very good. Yeah, you're getting the idea. Right. Indexing, I'm not really going to talk about indexing very much, though, and nor about narrowing, because I want to keep going. Otherwise, we will definitely run out of time. Right. Okay. So the next, so that's choice, right? That was verse 2. Verse 3 is functional logic. But what is functional logic programming, right? So in Haskell and ML, and more than any functional language, I'm going in the wrong direction. A let binding brings X into scope and says what value it is bound to, possibly lazily evaluated in Haskell, but equal, right? So the bring into scope and the give value are done at the same time. But in verse, you can separate these things, right? So in verse, you can do bring into scope and give value. You've seen that, it's spelt colon equals, right? But you can also do this. You can say bring X into scope, which I've just written as x colon int. And somewhere later, you can say, and by the way, x is equal to 3. All right? So I've separated bring into scope from give value.
But ordering doesn't matter, right? So you don't need to do this, do you?
You don't need to do this, but you can. And you might say, why do I want to do this? Well, it's because you could even pass x to a function that said that's equal to 3. It's all very first class. You'll see. Okay? So, yeah.
Can I then later say x equals 4?
Yes, you can later say x equals 4, and then x equals 3 and x equals 4. Oh dear, no values satisfy that. Fail. The whole thing returns 0 values. So absolutely, yes. So the way to think of it is, so here's the way we think of it, that this x colon int is really bringing x into scope. And I'm going to write that there exists an x, right? And then I'm constraining x here to be 3. And by the way, in this we're just getting a little flavor of the type system, I'm constraining x to be an int here. So I'm giving 2 different constraints on x. And int, actually that's just a function. which applied to x fails if x is not an int. All right? So types are functions, but we're not going to go much further with that. I just want to say that in verse you can bring x into scope and subsequently constrain it with equalities. Yes, David.
Can I say f colon int arrow int, and then later say f of 5 equals 17?
So now you'll get, so the question is, can I say f has type int arrow int, and then say somewhere else, say f of 5 equals 17? Pass. Right, so this is about equality of functions, and I'm not going to go there yet because because we could spend all day on that. So it's the right question to ask, but it's too early. Yeah.
Do the constraints fail at compile time or runtime?
Do the constraints fail at compile time or runtime? Absolutely runtime, right? So you might statically say, x equals 3, x equals 4. This is definitely going to fail, right? That's an effect, right? So you might say, this computation will definitely fail, but it's definitely a runtime thing. Yeah. Yeah. Can you use verse to solve differential equations? I have no idea, but maybe give it a try. I somehow doubt it. I mean, it's not magic. It's just going to be unification. Yeah. Louder, please. Why do we have to bring x into scope explicitly and not infer it? Well, so in fact, you don't. I've written it like this. So somewhere you've got to say, I'm bringing x into scope. So you can say x colon int back over here, but somewhere you have to say in what scope is x bound? Is it here, or is it out here, or is it way further out here? And that's done with a colon operator. That wasn't a very clear answer, but somewhere you have to say, I want to bring x into scope in this region of the program. Yeah. What's the difference between x colon equals 3 and x equals 3? X colon equals 3 is short for exists x dot x equals 3. So the colon, that's right. So you're exactly right. Colon is the clue that says, I'm bringing x into scope, and equals is the clue for I'm constraining it to be equal to this value. So colon equals brings into scope and sets it to be equal. Yeah.
So it would also be possible to write this int bracket x to define the type but not bring it into scope. Or is that not a real syntax? Can you declare the type without the colon, so without bringing it into scope?
Can you declare the type of x without bringing x into scope? No. No.
Because there needs to be unification scope.
Yeah.
But then why do we use e and dot instead of x?
Why do we use e and backwards e and dot instead of x semicolon? Because in the semantics, when we're designing this core language, which we're going to get to, we want to compose it out of minimal orthogonal features, and existential is it's been all over mathematics since the beginning of time. So it's a very standard construct to say to use it's like existential and for all. Use the for all from Haskell types, and even existential. It's that existential actually. Yeah.
If types are functions, but that means also functions are types.
So if types are functions, then what kind of functions are function types?
Can I define factorial as a type?
Can you define factorial as a type? I'm not going to go there because I either have to say a lot more or nothing, and I'm going to say nothing. Sorry. Yeah.
In the second example, could you write x greater than 3 constrained to a value?
Oh, could you say x bigger than 3? That's a really good question, right? So in a constraint logic programming language, you could say x is a value, and then you could say x is bigger than 3, and then you could say x is smaller than y, and then you could do all sorts of, fancy arithmetic proofs around it. Verse does not do that. So verse has very special treatment for equality, but it is not a constraint logic programming language with sort of built-in domain knowledge about arithmetic. Though x bigger than 3 will be stuck until somebody else gives an actual value to x. And of course, that all has to be expressed in the semantics too. But it's a good, excellent question, yeah.
X colon int and then x colon float, for example, would it be a compiler or would it?
If you say x colon int and x colon float, yes, you're bringing x into scope twice and it will become plain. Yeah. Say it louder. Can you have an uninitialized variable? Well, of course here, this exists X, that looks very like an uninitialized variable, doesn't it? Yeah. And so, in fact, here's an example, right? So, look, like this is just a programming convenience thing in Haskell. If we want to set y and z depending on the value of x, then you can say the pair yz is if x equals 0, then 3, 4, otherwise 232, 913. It's a bit clumsy, right? But you have to do all this positional matching up, right? To say, oh, the pair and the then branch, oh, the 3 comes with the y and the 4 comes with the z. So in verse, you can say x and y, are integers, and then you do the conditional, and then you emit the constraints for y must be 4 and z is 4 in the one branch, or the other way around, okay? So in a way, y and z are uninitialized until you get to the if. Yeah.
Can you bring a name into scope without immediately giving it a type?
Can you bring a name into scope without giving it a type? No, but the type can be any. And in fact, the intermediate language I'm about to show you is untyped anyway, so yeah.
Can you use choice syntax to bring types?
Can you bring an existential to bring a type into scope?
Can you use the choice syntax for the types?
Oh, can you use a choice syntax for a type so you can say x has type int or float? Actually, you kind of can, yeah. Because types, it turns out, are values. So that's a very interesting question, yes. Sorry, but I'm not going to...
Yeah, back to the uninitialized question. If I say there exists x, x is an int, no further constraints, wouldn't that just be choice of any integer?
Oh, yes. So what happens if the whole expression was exists x, x is an int, right? That yields rather a large number of values. Yes. And so you might say, and if I say if exists x, x is type int, does that succeed or fail, right? So that's a good question, right? Because now there are sort of too many values, not just a finite number of choices. So we banged our heads around that for a long time. The answer is it will get stuck. And again, we need a semantics that says why and allows programmers to reason about it. Yeah.
Is that type int bounded, or is it big num?
Are these big nums, are these integers? Yes, I think they're big nums. I'm not quite sure, but I think so, yeah. What happens if you use an uninitialized variable? Oh, okay, so that's similar to the this question here. What happens if we had x bigger than 3? So that, because we're not a constraint logic language, that has to wait until x gets a value. So if we got x bigger than 3, it'll just get stuck until somebody else gives a value to x. And if nobody gives a value to x, it'll just be stuck forever. So that's one way in which programs can not terminate, they can just get stuck. It's a bit like x equals x plus 1 in Haskell, right? Sort of black hole.
And that's a runtime error.
Yes, so the whole program will lock up and say, there's a little bit of haziness about what kind of error it is, but it will not execute and give you a value here. Yeah, one more, and then we're going to move on. Yeah.
Just to confirm, so if you use for and x as an uninitialized value?
Louder?
If you use for on an uninitialized value, it will get stuck.
Oh, yes, if you say x colon int, semicolon, 4x, then it'll get stuck, yes, because it doesn't know how big an array to make. In fact, the array would be rather large, yes. It'll be stuck. Okay, now, so look, we can go on to give these logic variables. This is, we're getting more towards the kind of things you might do in Prolog, right? So here, I've said P is a tuple of ints, a pair of ints, and then we said the first to P is 3 and the second to P is 4. So, these two separate constraints gave values to little pieces of X. Or we could say, oh, look, P is a tuple, and then we can say, oh, P is also equal to a pair of 3 and Y. And what's Y? Oh, that's just some other integer. And here I say, oh, P is also equal to a pair of Z, 4. So this, going back to Andres' question, here are two equalities on P, but they're not contradictory with each other. In fact, we do them both, then we learn the values of P and Y and Z. Okay, so, and these things are completely first class. You can first here is not a magical built-in thing. It's just an ordinary function. It's an ordinary function that takes a P, and it arranges in its right-hand side. It simply constrains P to be a pair and returns the first component of the pair, and then what happens when I call first? I'm passing this as it were uninitialized P. And inside first, it constrains it to be. Yes, David?
If I had a tuple of any, so tuple any,
yes.
A tuple indent, and I have an if that branches on whether the first projection of that tuple is an int,
buffer overflow. It was a question about tuples of any and that involved types again.
So the types of things that succeed or fail when passed a value, right? So
Ask me later. Yeah, sorry. Yeah, otherwise we'll. But I want to get to rewrite rules before we run out of time, and because let's see, I'm going to skip this as well. Right. But yeah. Let's see. So verse clearly can't be strict because of this sort of ordering things. You know, we continually talked about, you know, an expression might give a value to x, y. Maybe it could be completely strict, but it absolutely isn't. But it can't be lazy either, because what if a computation that gives a value to x is in something that hasn't been strictly evaluated? You know, so in a Haskell, it's a bit like in Haskell we can't make Haskell have I/O, impure I/O, because then whether or not something is evaluated affects, what we print. We don't like that. That's why we have monadic I/O. So here, with verse, in order to make sure that all these constraints get found eventually, it can't be lazy, right? So in fact, verse is lenient, which is what an old data flow language called id was lenient in this same sense. Okay. Now. So I want to spend just the last bit. So I think I'll just carry on for a bit, if that's all right. I want to spend the last bit of the talk, in the last 10 minutes, just showing you a bit about how. So Tim explains all this to us, and Leonard and I beat our heads against walls and say, what on earth does this mean? And so we've got to figure out a way to give a precise semantics to a slightly weird language like this. How can we say for any program what it does? So here's what we did. Of course, we started by defining a core language, a sort of minimal, like inside GHC, there's a core language that we translate the giant Haskell into this small core language. It's just the lambda calculus. Plus let and letrec. So for verse, we got a core language that we called the verse calculus, and we're going to translate verse into that, right? So, and here it is. So it's not very big. It's in the ICFP paper. It's on my homepage. I'm not really going to pause here. I just want to show you to say this is the syntax of the core language, and it fits on a little part of one slide. It's really quite small. Right. And so then we're then going to desugar this core language, desugar the surface language into the core language. So here's a tiny example of desugaring. Here's one of those, a kind of program of the kind that I was writing before. And here I'm desugaring. There exists an x because x is being brought into scope. No type here, so the types are a bit in fact, I've forgotten about types over here because I didn't want to talk about types. And then x is equal to what? Well, a 2, y. And where is y bound? It's bound by an exists. And here I just bound it, in this desugaring, I bound the exists y's right in this little corner here. And the same for z, and then I'm going to return x. So this is my desugaring. And then I've got to think of how do I execute this program? So execution, morally, is solve the equation. So I try to find values for all the existentials that make the equations come true. That's a good way to think about the execution model for verse. In fact, it was great to hear the CEO of a major, company on the phone to me saying, Simon, it's all very simple. To execute verse programs, you just have to solve the equations. And I'm thinking, you don't get many CEOs who tell you that, right? It's usually the other way around. So that's what we're going to do. We're going to solve the equations. Now, so operationally, I think you probably have got the idea that we're going to be doing unification, right? These existentials are going to be unification variables, and these equalses are going to turn into unification. But then we need to think about updating unification variables and occurs checks and backtracking and who knows what kind of carry-on. That's a little bit difficult for programmers to think about. So I don't want to have to talk about unification directly to programmers. So let's pick a book, take a leaf from how we describe the semantics of Haskell programs. Well, we do it by to end users, we don't say there's this STG machine and it has this stack and this heap and these heap objects with info tables. No, we just say you do rewriting. So here's a little example. I'm here saying we've got a function foo, which is x of x plus 1. So here's my expression foo of 3 plus 2. I could rewrite that by, this isn't, of course, the order of rewriting is not what, when GHC executes the program, it'll pick a particular order, but it's fine for a programmer to say foo of 3 plus 2, I can rewrite the 3 plus 2 to 5. Then I can inline foo and get 5 times 5 plus 1, then I can evaluate the 5 times 5. This is a perfectly good execution. Or I could inline foo right away here and get a let x, this x, equal 3 plus 2 in, there's the body of f, and then I could evaluate this in more than one way, because I could either substitute for the x and duplicate that 3 plus 2, or I could evaluate, you get the idea, right? So this is very, very standard stuff. So the idea is that the rewrite rules, rewrite equal programs to equal programs. You can apply any rewrite rule at any time, at any place in the program, and get a program that means the same thing. But that if you keep applying rewrite rules, wherever you start, you'll always end up at the answer. So they have to be confluent, right? Good word to impress your friends with if you don't know it. Confluent means if you rewrite along different paths, you can still rewrite to get back to the same thing. You won't get to different answers. So we're looking for a confluent set of rewrite rules. So we're going to just try to do a rewrite semantics for verse. And interestingly, there's a lot of literature on functional logic programming. So tell me, anybody, if you know a counterexample to this. I don't think there is a deterministic, rewrite semantics with this property that I describe here for functional logic programming. It's amazing. So, but here is one. So here's the kind of thing that we do. We distribute, then what might we do? Well, we might do something like, take these existentials and float them out. That should be meaning preserving. Right, now what do we do? Well, take this x and substitute, we got x equals 2y, substitute 2y for this red x. After all, if x is equal to 2y, then, this must also be the case here. So 2y equals z3. Now what can we do? Well, 2y equals z3, that could only be true if 2 is equal to x and 3 was equal to y, right? I could decompose this pair here. Now, of course, this is what a unifier does, but here it just looks like a simple rewrite rule. So that's turned into z equals 2 and y equals 3 here, right? Now, let me imagine replacing that x with, this 2y. So I'll substitute for x over here. So I've replaced that red x with 2y. Now I can replace that y. Well, I know that y equals 3. So replace that red y with 3. So I get 2, 3 down here. And now all of this existential and equations, they're just cruft. Now we can garbage collect them because the result of this program is 2, 3. Okay? Nothing up my sleeve. I didn't do, I was doing unification and so forth, but it was just declared by ordinary rewrite rules. So the thing, and you could do that by more than one path. The thing I want you to get the idea of here is that instead of having, a heap of heap-allocated unification variables and stuff, and backtracking and so forth, the heap is sort of reified in the term. All of these bindings, like here, these x equals 2y, in an operational model, this x equals 2y might be, some kind of heap with a pointer to the 2y pair. Here, it's just a little part of the syntax tree. So we put in the syntax of the term something that you could think of as the heap. And then unification is expressed by rewrite rules, and particularly substitution, right? But when you substitute, you might have wondered here, why did I choose to substitute for, this? When I substitute for this x, I could have substituted with z3, or I could have substituted with 2y. Here I chose to substitute with z3, right? But the idea is it doesn't matter which you pick. There's quite a lot of flexibility about which of these things you pick. Okay. And this idea of reifying the heap in the structure of the term comes from an old paper by Ariolo and her colleagues, Ariolo and Wadler again. Wadler often shows up in clever ideas. Papers called A Call by Need Lambda Calculus. I thoroughly recommend it. It's not a hard read, this paper, and it really gives an idea of how you can explain call by need evaluation using rewrite rules, and we're just leveraging the same idea to do functional logic programming. So, in the last 4 minutes, I was going to show you a sort of like a video stream for, flick, 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 rewrite rules. I just want to give you the idea, just the idea of some of the rewrite rules. Here are the, here, for example, is a unification rewrite rule. It says if you've got a tuple v1 to vn equal a tuple v1 prime to vn prime, then I can rewrite that to, well, a bunch of equalities. That's what you saw that happening, right? That's just a simple rewrite. You can do that anywhere. If you have k1 equals k2, then you can rewrite that to just e, but if that succeeds. Does that succeed? It succeeds if k1 is equal to k2, and so forth, right? And there are quite a lot of these. How many rules do we get? I'm not going to have time to talk about substitution. There's stuff about, look at beta. This is the beta rule. And now let me point more towards you. This is nice. Lambda x dot e applied to v. How do we do that? Well, just like in the lambda calculus, we essentially make a let. We could say, let's turn that into exists x, a constraint that x is equal to v, and then the body of it. It's really very simple. There's quite a lot of rules that are, and this appears in the Areola paper as well, that sort of move things around. Right. So what have I got here? I've got, here I've got y equals x, and I want to switch it to x equals y. Here I've got an equality that I want to move to the front of the expression. There's quite a lot of sort of commutation rules, and it's tricky to get those right. Yeah. Do we make sure that we don't go into a loop? In one way, it's not bad to go into a loop, right? These are simply rewrite rules that say these two programs are the same, but we would like them to be directed so you can, as a programmer, if you like, just use them in a particular order and always get closer to the answer. So, in fact, we can modulo recursion, yes, but they are directed and you won't go into a loop. But there's a, to get that exactly right, that's quite delicate. Okay. So, Farhad is appearing in a threatening kind of way. So I'm not going to have time to talk about flexible and rigid variables and one and all, which are super cool, but they're in the paper. So, and all about choice. All I can say is, these are all the rules, right? They fit on one slide, one page, but there are still quite a lot of them. So if you want to prove this set of rules confluent, that is quite a big job. And it turns out that initially it just wasn't true. So Ranjit Jala has lost a lot of hair proving this, and Guy Steele is even now proving a property called skew confluence about this. So it's a substantial piece of work here, but at least they're of the kind of scale which you can actually execute by hand. And we really do. Rather than saying to Tim, what does this program do? We just run the rules. And we have lots of quick check properties and implementations of rewrite rules. It's great. To finish up then, there's a lot more that I haven't talked about, I/O and effects and transactional memory and struct and class. Don't talk to me about that. And particularly the type system, right? We talked a little bit about types, and I thought I might have 4 minutes to talk about types, but I don't. Types are just values. They're just functions that can fail. So it's int is a function that fails on non-ints and succeeds on ints and is the identity function. Array of int is a function that succeeds on arrays, but it applies the type argument to all of the elements. So array is itself just a function that takes a type and produces a type. It's all very nice, actually. But to type check it, of course, we then, since they are functions, we need to execute verse programs in our head. The type checker needs to do that. And clearly that gets into undecidability land, so that's why we call it the verifier. No. So this is my last slide. I want to say, I think you can see here that there's something pretty interesting going on. I think it's interesting and exciting. We'll have to see whether the aeroplane falls out of the sky, but I'm pretty optimistic about it. But there's a lot of crazy stuff we're trying to do here and get right at once, all this stuff about transactional memories and types. But the sort of takeaway message that I like to have is that there's something interesting, and it's a kind of open project. And increasingly, I think we'll try to push stuff not just in the form of papers, but actually artifacts that you can play with. Because I think we're opening up a sort of whole new, just as functional programming opened up a whole new sort of space of intellectual endeavor that meant that people in industry write papers with co-monads in the title, or write blog posts with co-monads in the title. Same might happen here. It's proving to be a lot of fun. So that's it. Thank you very much.